A frequency synthesizer is an electronic system for generating any of a range of frequencies from a single fixed time base or oscillator. They are found in many modern devices, including radio receivers, mobile telephones, radiotelephones, walkie-talkies, CB radios, satellite receivers, GPS systems, etc. A frequency synthesizer can combine frequency multiplication, frequency division, and frequency mixing operations to produce the desired output signal. 3 types of synthesizer can be distinguished. The first and second type are routinely found as standalone architecture, direct analog synthesis, and by comparison the more modern direct digital synthesizer. The third type are routinely used as communication systemic building blocks. Indirect digital synthesizers including integer N and fractional-N. It is in some ways similar to a DDS, but it has architectural differences. One of its big advantages is to allow a much finer resolution than other types of synthesizers with a given reference frequency. Prior to widespread use of synthesizers, radio and television receivers relied on manual tuning of a local oscillator, which used a resonant circuit composed of an inductor and capacitor, or sometimes resonant transmission lines, to determine the frequency. The receiver was tuned to another frequency by either a variable capacitor or a switch which chose the proper tuned circuit for the desired channel, such as with the turret tuner commonly used in television receivers prior to the 1980s. However, the resonant frequency of a tuned circuit is not very stable. Variations in temperature and aging of components caused frequency drift. Automatic frequency control solves some of the drift problem, but manual retuning was often necessary. Since transmitter frequencies are well known and very stable, an accurate means of generating fixed, stable frequencies would solve the problem. Quartz crystal resonators are many orders of magnitude more stable than LC circuits, and when used to control the frequency of the local oscillator offer adequate stability to keep a receiver in tune. However, the resonant frequency of a crystal is determined by its dimensions and cannot be varied to tune the receiver to different frequencies. One solution is to employ many crystals, one for each frequency desired, and switch the correct one into the circuit. This brute force technique is practical when only a handful of frequencies are required, but quickly becomes costly and impractical in many applications. For example, the FM radio band in many countries supports 100 individual frequencies from about 88 MHz to 108 MHz. Cable television can support even more frequencies, or channels over a much wider band. A large number of crystals increases cost and requires greater space. Many coherent and incoherent techniques have been devised over the years. Some approaches include phase-locked loops, double mix, triple mix, harmonic, double mix divide, and direct digital synthesis. The choice of approach depends on several factors, such as cost, complexity, frequency step size, switching rate, phase noise, and spurious output. Coherent techniques generate frequencies derived from a single, stable master oscillator. In most applications, a crystal oscillator is common, but other resonators and frequency sources can be used. Incoherent techniques derive frequencies from a set of several stable oscillators. The vast majority of synthesizers in commercial applications use coherent techniques due to simplicity and low cost. Synthesizers used in commercial radio receivers are largely based on phase-locked loops or PLLs. Many types of frequency synthesizer are available as integrated circuits, reducing cost and size. High-end receivers and electronic test equipment use more sophisticated techniques, often in combination. A well-thought-out design procedure is considered to be the first significant step to a successful synthesizer project. In the system design of a frequency synthesizer, states Manasuich, there are as many best design procedures as there are experienced synthesizer designers. System analysis of a frequency synthesizer involves output frequency range, frequency increments, frequency stability, phase noise performance, switching time and size, power consumption, and cost. James A. Crawford says that these are mutually contradictory requirements.